Okay.
Okay. Okay, so we have the pleasure to have here with us today Dr. Evangelia Samara. Evangelia studied in the National Capodistran University of Athens and then moved to Leuven, to KU Leuven, for her PhD diploma, thesis, yes. And then moved to NASA Goddard Space Flight Center with an NPP, right? So the title of her talk today is Time-Dependent Solar Wind Simulations in the Inner Helisphere, Advances and Challenges. So Evangelia, thank you.
Thank you very much, Thanasis. Hello, everyone. I'm very happy to be here today and share with you part of my work that I'm currently focusing on. So let me start the full view. Okay, so my research interest in general is the improvement of the solar wind forecasting and modeling in the inner heliosphere. And I'm trying to do that from many directions with different models and also by employing different kinds of observations. In this talk today, I'm going to talk about part of my work which has to do with improvements that we want to make in the frame of the so-called time-dependent solar wind simulations. Όλα okay, με ακούτε? Okay. And I will explain what time-dependent solar wind simulations are in the next couple of slides. And of course, I want to devote quite some time on describing the advances that we get thanks to these simulations, but also the challenges that we are encountering in the process of doing that. So I want to start the presentation by first introducing you in the solar wind modeling concept, how solar wind models work. And of course, I'm going to describe a little bit the models that I am working with. However, I have to admit that the types of models that I'm working with are also being used by the majority of people in the community. So you will get, I think, a good idea of how things are done. Then I want to devote most of my time describing the time-dependent simulations and comparing these time-dependent simulations with the older way of doing stuff, the older way and the older approach that we used to do, and we are still using, of course, because the changes cannot happen overnight and suddenly switch from one approach to the other. Has to do with the so-called steady-state approach that I will show you in the next slides. And I'm going to explain what the limitations and the restrictions of this older approach was that obliged us in a way to move to a more to the new approach and to see things a little bit differently. Of course, I will talk about the challenges because whenever we do stuff, of course, we always encounter problems and we need to deal with the problems, and we're always learning more if we're dealing with the problems. And I want to finish my presentation by sharing with you some very preliminary results that I have with the so-called synthetic, namely fake white light images that me and my team have recently constructed based on some time-dependent and steady-state modeling output that we will use as a preparation for the upcoming PANCE mission that I will also explain what the PANCE mission is. So let me know if you see or if I should go away. When we want to forecast the solar wind conditions and properties in the inner heliosphere, we cannot do that by just using a single model. And that's because the physics is different, going from the sun further away. Different processes dominate closer to the sun and different processes dominate further away from the sun. So in this very simple schematic that I try to adapt a little bit, and of course it's not in scale, I'm showing the two major domains that we split the inner heliosphere in order to use different models at each part to reconstruct the conditions there and eventually get what we want, namely the properties of the solar wind wherever we want in the inner heliosphere. So the first part is the coronal part, which extends from, I will show it also here, from the photosphere of the sun until 0.1 AU, and then we have the heliospheric part that extends from 0.1 AU onwards. The corona, we assume, of course, that it is magnetically dominated, while the heliospheric part, we assume that we have the solar wind being propagated always outwards in supersonic and superalbenic way. And we also, of course, take into account that the magnetic field is frozen into the plasma there. And as I said at the beginning, since we do this discrimination, we have to use different models. And this is the highest level of the models I'm gonna show you today. I don't need to go into details, but it's just important for building the story today to keep in mind that for the coronal part, we use the so-called WSA model. It's WSA, they are acronyms from the names of the main three developers, Wangxi and RG. It's a semi-empirical model. It uses physics and some assumptions in order to reconstruct the magnetically dominated corona. And the most important thing, to produce a set of boundary conditions at 0.1 AU that are necessary to be fed into the heliospheric part, to the heliospheric model afterwards, and start the propagation of the solar wind. For the heliospheric part, we use the so-called GAMERA model. It's a 3D MHD code. And for more information, you can ask me later, you can see the citations and so on. Now, this pipeline of models is being driven by what else? The magnetograms that we all know. And I need to emphasize, and I'm sure most of you know, that if our magnetograms contain errors or if they have uncertainties, all those uncertainties are going to be propagated outwards. And please keep that in mind for the story that I'm going to share with you afterwards. Now, in this slide, I will describe more or less the same things that I said before, but it's a more visual way for you to understand better what is the input and what is the output. We all know the magnetograms on the left-hand side of the slides. We use magnetograms. I specifically use the GONG-ADAPT magnetograms to drive the pipeline of models. And then these magnetograms are being fed into the WSA coronal model and produce in order to produce the boundary conditions at 0.1 AU. And what are those boundary conditions? I have an example here of such boundary conditions. It's like this velocity map and radial magnetic field map, namely the radial velocity of the solar wind and the radial magnetic field at 0.1 AU. Blue colors here mean slower solar wind, which is mostly extending around the heliospheric current seed. Red colors mean faster solar wind. And here is an indication of the magnetic field polarity, light gray positive polarity, dark gray negative polarity, and the shape of the heliospheric current seed, you see it here in the yellow line. I'm not sure if it's very visible, but it doesn't matter. And this is an example of the boundary conditions that are produced by the WSA, and when are fed into the heliospheric GAMERA 3D MHD code, this is one of the output we get, namely, this is the solar wind speed in the inner heliosphere, in the equatorial plane specifically. The colors are similar to what I said before. Blue means slower wind, green and red means faster wind, and everything rotates in a steady state manner. And of course, we want to evaluate the output out of these models. And one of the most direct way to do that is to compare our modeling output in the form of time series with the in situ observations that we get from the spacecraft all around the inner heliosphere. And we are very lucky nowadays because we have a couple of them orbiting the sun. And these are just examples of the comparisons I'm doing regularly between modeling output and observations that are always shown in black for different kind of spacecraft. And but I need to say that if we want to evaluate properly what is happening here, because sometimes our models perform well and sometimes our models perform badly, we need to apply appropriate metrics. But I'm not going today into the story of the metrics, which is a very interesting story. What I want to say before introducing the time-dependent solar wind simulations to you is the fact that the traditional way of doing things is we take one magnetogram and we drive the whole pipeline for a couple of days, couple of weeks, sometimes for a full calendar rotation. And the magnetogram is nothing more than the image of the sun for that specific moment. So if we use that to run predictions for a couple of weeks, we shouldn't expect that our predictions would be reliable, right? Because we have because the sun and the solar corona is evolving. We have coronal holes opening up, closing. We have active regions emerging and go down, and all these dynamic effects cannot be captured by only one magnetogram. So that's why the time-dependent solar wind simulations come to the table. And let me explain to you what we mean by that. Instead of giving one magnetogram to drive the whole pipeline, we give a sequence of photospheric maps with a cadence of whatever it interests us, depending on our goals, every 24 hours, every 6 hours, every 2 hours, up to the availability of the magnetograms we're using. This sequence of magnetograms is being fed now into the WSA model that produces in turn a sequence of boundary conditions of 0.1 AU. And this sequence of boundary conditions now are being fed into the heliospheric 3D MHD GAMERA code to give us a much more realistic evolution and propagation of the solar wind in the inner heliosphere. And I hope you see the difference with the previous video that I played, but just to make my statement better, I have here the two videos, one after the other, one in the steady state and the other one in the time-dependent approach. In the left-hand side, you see what happens if we use one single magnetogram to forecast stuff for a couple of days or weeks. Whatever is slow in the boundary remains slow, whatever is fast in the boundary remains fast, and it just rotates in a steady state manner. While on the right-hand side, what we have is a dynamically evolving solar wind with new information continuously emerging from the boundary. And when I say boundary, I actually mean this white sphere that you see in the middle. And I hope you agree with me that this is a much more realistic approach of modeling stuff in our inner heliosphere, since conditions continuously change all the time, and especially in the solar maximum. And another thing that I find very interesting is this comparison of specific timestamps of the heliospheric conditions at exactly the same time with the different approaches and different cadences in magnetograms. The left is what I said before, the traditional steady state with the perfect Parker spiral and things that never change. However, the second, the third, and the fourth are print screens of the solar wind in the inner heliosphere in the equatorial plane. As we update our magnetograms and thus our boundary conditions every 24 hours, every 6, and every 2 hours. And the very interesting thing to see here is that the more frequently we update the magnetograms, the finer structures we get in the model solar wind. And that's important for the future, because if we are happy with the background solar wind that we are modeling, then we will be more confident to launch the more eruptive and extreme events such as CMEs, and to minimize the errors that in our modeling approach, at least as far as the solar wind is concerned. Okay, and well, I said so many things about the time dependence, about the time-dependent approach, but do you believe me? And eventually, do we really get better results when we are predicting the solar wind conditions in the heliosphere? And the answer is coming first from a number of comparisons between time series from observations and modeling output. What you see here is different plots of solar wind properties, beginning from speed, density, Bx, By, and the so-called phi angle. Phi angle, I mean as phi angle, the longitudinal angle of the interplanetary magnetic field, which has predominantly two directions. I will explain in a moment what this is. But what I want you to see, black, by the way, it's always observations, blue is the time-dependent approach, and red is the steady-state approach. So if we see better the first panel, the speed panel, of course, you will notice the same as me, that this first part of the calendar rotation, because I forgot to say that this is a full calendar rotation, it's a full month of September 2021. And the first part of this calendar rotation is super failing, no matter the approach we are choosing. And I will explain at the end why this happens. However, I hope you agree with me that for the rest of the period, the blue time series performs much better than the red time series. It captures the high-speed stream here. It captures the slow solar wind here, and the transition from slow to fast wind here. Opposite to the red time series, which, well, it's only one magnetogram that they used for the whole month, and the conditions were not updated, so it was wrongly predicting stuff all over. We are generally quite happy with the way the rest of the signatures are being modeled and predicted. I want to focus quite a lot on the last panel, which is the phi angle. Well, I said before that this is the longitudinal angle of the interplanetary magnetic field. It is very simplistically shown in the plot on the left. You see like how a perfect Parker spiral is formed between the sun and the Earth, that is shown with the blue circle. And I have noted the geocentric solar ecliptic frame with the red arrows, because it does play a role to understand if the predominant direction of the interplanetary magnetic field is towards or away from the sun. And if it's towards the sun, it shapes an angle of approximately 315 degrees with the GSE frame, but if it's away, it shapes an angle of approximately 135 degrees with the same frame. And if I go and predict the phi angle with my steady-state simulations, I will see exactly that. I will see that my phi angle is this ideal either outwards or inwards, exactly as we explained in this schematic here. It's either 135, it's either 135 or 315, and it's so different and so far away from the real observations and the in situ data that we get from ACE, that we know things are not that way, right? And to give you an idea of the 3D representation of what we see in our modeling structures, I traced a bunch of magnetic field lines from the Earth back to the inner boundary. The inner boundary of the domain is shown here, color-coded based on the solar wind speeds. It's the map that I showed you before, but now it's like in a sphere and not opened in a map style. And you see this perfect Parker spiral going from the Earth to the inner boundary, and this cannot be changed. However, if I try to predict the phi angle by doing time-dependent solar wind simulations and updating my magnetograms, and thus my boundary conditions every 24 hours, you see with the blue time series that I'm doing much better. It's still far from perfect compared to observations, but I'm doing much better compared to what the red line was doing. Especially here, I captured very well the fluctuations of the phi angle, the sudden increase and sudden decrease here. And again, not everything is perfect, but we are closer. And if I do the same predictions with time-dependent simulations, but updating my magnetograms every 2 hours, I'm getting the magenta line that it's even closer to observations. And why this is important and how this is to be explained. If I trace now my magnetic field lines from the Earth back to the solar, to the inner boundary, at 0.1 AU, I will see that my magnetic field lines, they date a lot from the ideal Parker spiral. You see that in the GIF here. They warp in themselves, they fold in themselves, they change directions. And that's the main reason that we were obtaining the better predictions before. Why this is the point? Why this is the case? I'm sorry. Because as I change the boundary conditions at 0.1 AU, so I update regularly the solar wind velocities at that specific sphere, plasma parcels of different speeds are moving on top of the same magnetic field lines. So again, with colors is the solar wind speed. Blue means slower speeds, red means faster speeds. So if plasma parcels of different speeds move on top of the same magnetic field lines, and the magnetic field lines are frozen into the plasma, that means that they follow the movement of the plasma. So they wrap in themselves, they fall, they change direction exactly because of depending actually on the flow speed. And that's a very nice effect, physical effect that we can capture with our simulations, something that can only be seen in the time-dependent simulations. And not only it's important because it gives us better signatures, in situ signatures, as I showed in the previous slide, but it's very important because that way we will also be able to improve the solar energetic particle modeling. Because, well, we have experts here with SCPs. I'm not an expert on SCPs, but since SCPs are moving with the on top of the magnetic field lines, and if we can capture better how these magnetic field lines deviate in direction and also how their length is changing, then I have high hopes that we will get very promising results for the future SCP modeling in general. Very quickly, I'm going to briefly show you some other advantages. Well, actually, to prove my point that time dependence behaves and gives us better results in a more statistical way, I did some statistics for different positions, for different spacecraft, so different positions in the heliosphere and for different current rotations. And what you see here is actually box whiskers plot of speed on the first plot, density, the second, and BR on the third plot, distributions. The first box is the ground truth. So the first box at each one of the plots represents the ground truth, with the red line representing the median of the speed distribution or density distribution or BR distribution. The upper and lower parts of the box showing the first and the third quartiles of the distributions, and the legs showing the values that are beyond the first and the third quartiles. And I put next to them what are my distributions with the steady state and with the time-dependent approach for all the parameters of interest, and for speed and BR. Again, it's not perfect, but it's much closer to the ground truth compared to the steady state simulations. I hope you see the same with my histograms here. With the steady state that is always indicated in yellow here, and with the time dependent that is indicated in red, we see, for example, overestimation of velocities here that shouldn't exist, and they don't exist in the time dependence. We see that steady state doesn't capture low to medium values, while the time-dependent approach does. The same with the BR here. The red distribution is a bit better than the yellow distribution. However, we do have some discrepancies with density, and that's why I left it for the end. With this statistical approach that I wanted to evaluate my results, I find that, well, it seems that the steady state captures better the observations. However, if we go current rotation by current rotation and we see what is happening there, the reason why the steady state simulation, like the steady state box whisker plot seems to be better here, is because the peaks, the density peaks that we get in our time series are actually overestimated. They are correct in time. We capture the low values of the density very well, opposite to the steady state approach. However, the density peaks when we have them, because, for example, we have stream interaction region approaching. It's overestimated, and it's something that we should fix. Something quickly here as well, since I'm only doing solar wind right now, one of the most interesting phenomena to study in the solar wind are the stream interaction regions, namely the compression regions that are being developed when the fast solar wind overtakes the slower solar wind ahead of it. And I thought it would be interesting to do some superposed epoch analysis of these stream interaction regions. So I took a number of high-speed streams. I took as zero epoch the density peak that precedes the increase in density and in temperature and in magnetic field once the fast flow arrives at the position of interest. And based on my zero epoch, I wanted to see how the profiles of the stream interaction regions were behaving in the time-dependent and in the steady-state approach. And I hope, again, that you agree with me that in the time-dependent here, the profile is it's actually very close to what is observed compared to the steady state, which is this blue line. The same for the density, and the same for the BR, which is, again, still not perfect, but much closer to observations compared to the straight blue line that we were getting from the steady state simulations. And now it's the time to talk about the challenges that we encounter. And the main challenge that we have is actually some issues that we get because of the frequent update of the magnetograms, which is necessary to do this time-dependent approach. So what happens is that we have observed a number of artifacts being generated in the heliospheric domain, exactly because of abrupt changes in the magnetic field from one magnetogram to the other as we're changing them. And abrupt changes in the magnetic field can happen because, for example, we can have an active region suddenly appearing in the east limb of the sun. So in this slide, you see an example of what I'm saying here. On the left, it's a magnetogram of one random day, the 24th of August. And the right magnetogram is the magnetogram of the next day, the 25th of August, in which you see the sudden emergence of active regions from the east limb. And well, this sudden appearance, as we do not know that this information is coming, can lead to can disrupt a lot the magnetic field topology that is reconstructed by the WSA coronal model that I was saying before. So when we want to reconstruct the magnetically dominated corona and understand where we have positive polarity, for example, or negative polarity, based on these maps on the bottom, you will see that the heliospheric currency, for example, in the first case, is quite flat as we can say it is. But in the second case, once the active regions emerge, then you will see this sudden drop, this sudden warp. And going from the one step to the other, this is the reason that these artifacts are being generated. And to give you a better idea of what these artifacts are, I'm presenting them in this slide. These maps are the so-called latitude-longitude maps, or CATs, better, of the radial magnetic field, but not at the inner boundary, at Earth. So in the steady-state approach, what we have on the left-hand side is, since we did everything with only one magnetogram, we know what the magnetogram gives us, like specific predictions for the positive polarity in red, the negative polarity in blue, and specific structure for the heliospheric currency that is shown with this black line. And the different satellites with which we're interested to, on which we're interested to predict our conditions are projected to either the one or the other polarity, and so on. But when we do that in the time-dependent approach on the right-hand side, and since we are updating the maps continuously, and since the maps from one day to another can be a little bit different, or we have an unexpected appearance of new information, or we even not have all the information. Sometimes we have, for example, a monopole arriving because we only see the first part of the active region and we don't know what will come afterwards. And this disrupts quite a lot the topology that I was saying before. And the artifacts that I was trying to explain are actually these so-called magnetic field islands that are being produced. And they have opposite polarity compared to the polarity of the hemisphere they are projected to. Let me play that again. So this kind of islands here, and you see the heliospheric currency, it is really structured. It's one, and then it splits to many pieces, and we are not sure how much of this is true, how much of this is caused because of artifacts. And at this point, I need to say that some of these islands are not artifacts, but they should be there and they can be physically explained because they seem to be generated from the folding and the warping of the magnetic field lines that I was explaining before. So what happens is that if I take a magnetic field island here and I trace back the magnetic field lines to the inner boundary that I was showing you before, I will see that these magnetic field lines from these islands here are being connected to the pseudostreamer area in the sun, which is quite far away from the heliospheric currency, because you see here that also the heliospheric currency is here. It's quite far away from this kind of islands. So some of these islands, like those that are far away from the heliospheric currency, can be physically explained, and we want them to be there because they make sense. However, at the beginning of the movie, some other islands very close to the heliospheric currency, like here or here, and let me show them also for people online, very close to the heliospheric currency, could be artifacts. And this is a huge project to go in. It's not really straightforward to say which one should be there and which one should not. So we have submitted a proposal to try to go more in depth and figure out what's going on in the time-dependent approach, because we do not want to have poor quality of our time-dependent solar wind, and we cannot get entirely rid of these artifacts, but we can mitigate this effect. And something else that I found very interesting is the fact that, well, I showed you how with the sudden arrival of the active region, the magnetic field topology is being disturbed and disrupted. And I told you that the same happens when we have part of the active region going on. For example, in the left-hand side, you see the magnetogram with which, like, there is a monopole here, like only part of the active region seems to be apparent. And the magnetic field topology that has been reconstructed by the models is this specific one, but we know it's wrong because we're missing information, because we know that the other part of the active region is there and the information from the magnetogram is not complete. And based on this magnetogram and this magnetic field topology, we make a number of predictions. And in this case, we should expect the predictions not to be correct. Once the active region is fully immersed, you see again the shape of the heliospheric currency that has changed. And this part here should be more correct to the previous part. So we normally hope that then we will go back to a better quality predictions of the solar wind. And that's the reason that I told you at the beginning of the presentation that we were not able to capture this part, this first part of the cutting the rotation right. No matter the approach that we used, because the magnetograms were wrong in this case, and well, they were not wrong, but they did not contain the full information. The connectivities and magnetic field topology was not so correct, so we took wrong predictions. And there's nothing really we can do about it. And no matter how much we struggle to improve the models and to employ new techniques and new methods, unless we get better prediction, better observations to improve the first input in our modeling pipeline, this kind of stuff will never be able to get better. So that's why, in my case at least, I'm always hoping for a 4-pi mission around the sun that can give us a full view of the backside of the sun and of the poles of the sun, so that magnetograms can actually be improved and eventually get to give us better solar wind simulations and space weather simulations in general, not only solar wind. The last part, it's dedicated to these preliminary results that I mentioned about a number of synthetic white light images that we recently created. Well, everything started because of this very interesting launch of the PANCH mission that hopefully is going to take place next month. PANCH is a new mission. The acronyms of that mean polarimeter to unify the corona and the heliosphere. You see, more or less, like in an artistic/scientific way, how the PANCH mission is going to be like. It's a constellation of four different spacecraft. It's a NASA Small Explorer mission, and it will contain a narrow field coronagraph that will have a view between 6 and 32 solar radii. It will have a wide field imager, heliospheric imager, between 18 and 180 solar radii, field of view, and a student-contributed X-ray spectrometer. And the science that this PANCH mission wants to do is, in general, to determine processes that unify the solar corona and the heliosphere, as the name also reveals. If we split that down in more specific objectives, as the team says all the time, they want to understand how coronal structures eventually become the solar wind, and to understand the evolution of the transient structures such as CMEs in the young solar wind. And if you split down this objective even more, and you go, all the information are given in this link. You can go and get many more information for that mission. The sub-objectives out of this first objective is, for example, to measure time-dependent solar wind flows from the outer corona to the inner heliosphere, or it's also to determine the large-scale flow context that is necessary to relate the coronal structure to in-situ measurements. And a third sub-objective is, for example, to characterize the global solar wind conditions through which the transient structures are being propagated. And all those three sub-objectives fit very well within the frame and the content of my work, mine and my team's work. And that's why we wanted to be involved with the PANCH mission very much. And how are we trying to prepare for that mission? Well, when the mission is eventually up and running, the plan is to send a number of, I think it's every 8 minutes, it should send 7 images every 8 minutes. One of these images should be a polarized image, and the rest 6 of them should be an unpolarized images, or the opposite, something like that. So before we get the data from the mission, we wanted to understand from the modeling point of view, if we create fake polarized images, for example, what are we going to see there? Can we explain what we see there, at least from the modeling point of view at first? And these are my synthetic/fake, as we call them, white light images that have been created based on input from the GAMERA 3D MHD code. What you see on the first row is output from steady-state simulations. What you see on the second row is output from the time-dependent simulations. And let me now explain what its panel shows. The first column shows densities of the solar wind in the inner heliosphere at the equator, right? And there is a spacecraft at the left part of the image here, which for us now, for this example, was supposed to be the ACE spacecraft. And these long lines here show the field of view, which for this test, we chose that to be 120 degrees. So if we go and sit now at the ACE spacecraft and we see the sun in front of us, this is the image that we will get, namely the second column and the third column is exactly the same image that an observer will see as it sits on ACE and see in front of him the sun. In total brightness and in polarized brightness, they do not have much difference here. And I'm not sure if you really distinguish, but since what we see is density structures, which, by the way, the details, I hope you agree with me that the details for the time dependent is much more obvious compared to the steady state approach. You see in the equatorial plane that, again, we deviate from the Parker spiral opposite to the steady state one, that we see many more details. The solar wind is much more structured. And all these shades that we see here are actually stream interaction regions, are regions with increased densities because of fast flows encountering the slower flows in front of them. And I have a video that I hope it will show better things. So in this video, we have we are on top again of the spacecraft, and the spacecraft itself goes around the sun in an orbit around 1 AU. It's just circling the sun in the same heliocentric distance around the sun. So this is what the observer that does a flyby sees in the steady state approach, and this is what the observer will see in the time-dependent approach. I will play it once more. I need to really sit down and study all the details on these plots. That's why I said it's preliminary work. I didn't have the time yet. They were made a little bit before Christmas. I didn't have the time yet to really understand in detail what I see there. But this is the kind of images that eventually PANTS will give us. And we are very excited for that. And I think since the real observations are going to be much more noisy and much more detailed and with many more information, we need to understand first what the models can give us. And that's all. To get into the summary and conclusions, time-dependent simulation seems to be the future for more precise and realistic solar wind simulations and predictions. It's a great approach to analyze and understand the physics that take place in the inner heliosphere, opposite to the steady-state traditional way of doing things. The advantages that I discussed in the talk today have to do, in general, with more reliable solar wind predictions of almost all the quantities of speed, density, magnetic field, pi angle, exactly because of this continuous update of information that we get from the sun and from the solar corona. And this kind of simulations and improvement of background solar wind, we hope and we really believe that will lead to better modeling of the more extreme solar wind events, like the CMEs and the SEPs. We showed better reconstruction of the SIRs, the stream interaction region profiles, and one of the most significant physical phenomena that we see in our modeling in this time-dependent modeling approach is really the folding and warping of the magnetic field lines because of the plasma parcels moving in the same magnetic field line and magnetic field lines being frozen into the plasma, so they have to move and they have to follow the movement of the plasma. The challenges is, well, the fact that we need to mitigate these artifacts that I was talking about. We need to understand the percentage of them, how many they are, how big they are, while we're changing maps from one timestamp to another. And we have in mind already some ways to mitigate that, but this problem is not going to be solved. It's very hard to be solved, but it can be at least eliminated at some point. And last thing about the applications of what we're doing with future missions. It's very interesting what is going to happen with the upcoming PUNCH mission, and that's why we are preparing these synthetic white light images, and we're trying to identify what we see there. And this is also a way to appreciate the potential and the capabilities of the time-dependent approach. Thank you very much. So that's all, and I will be happy to take questions.
Great.
Thank you, Evangelia. Do we have any questions? Nobody?
Yes.
Yeah. Very nice question. I'm not in this field, but so when the magnetograms that you were showing, that is the initial starting point
Yes.
of everything, they are ground observation from.
Well, yes. The ones I'm using, it's from GONG, and GONG is a ground-based system of satellites, of observatories, I'm sorry, that they take the observations from the ground. However, I'm using GONG ADAPT. ADAPT, I'm not sure if you have heard of that. So we take the GONG maps, but on top of them, we apply a number of data simulation techniques. There is some flux transport models that they are applying, trying to evolve the flux on the background of the backside of the sun and on the poles. And they try to take into account phenomena such as granulation and supergranulation, differential rotation. So it's a much more improved version of the GONG, certainly. And this is the only thing I have worked with because of their easy availability and because, to be honest, my team also works with them. But there's nothing stopping me from using HMI, for example, or other algorithms.
No, just trying to understand one of the things that you mentioned about the observational limitations that you have produce this mismatch between your models and the observation. And I was wondering if, from what you were saying, is that obviously if you are observing from Earth, you will always you need to observe the whole sun, right?
Yes. But if you are in space, you can also not observe the whole sun.
That's what I was trying to understand.
So
you always have this limitation that your map is not real time, let's say.
Exactly. But well, if we get the L5 mission and now NASA granted the polar missions to go around the polar fields of the sun, and if all these missions eventually are combined, we hope that they will give us a better coverage of the sun, still not far from 100%. That's why I talked about the 4Pi mission, because it was actually a mission that was indeed proposed within the frame of the decadal survey. And the plan was to have 4 spacecraft orbiting all around the sun and have a coverage of almost 98% or something like that. But I don't think it went forward. Yes.
Thank you.
Thanks.
Thank you for the question.
You have a question? Yes.
I was wondering if you expect this model to have the same efficiency during the whole solar cycle. For example,
yes.
The solar minimum or solar maximum.
Right, that's a good question, because I mean, I didn't say everything, right? And when I presented the models that we're using, the WSA coronal model and the heliospheric model, the WSA model, it's again not one model, it's a combination of smaller models. And one of the most significant models that contain below it is the so-called potential field source surface model, the PFSS. And the BFSS, we know it works much better in the solar minimum rather than in the solar maximum. So this is, for example, one source of why I should not and we should not expect this kind of to have the same quality of predictions overall. Because it's a potential field and the sun is far from potential during solar maximum. So that's the main reason it should work better, and it seems to work better during solar minimum.
Okay, do we have any other questions here? Okay. I have a small question.
Sure.
Okay, so the time-dependent simulation that you're running, how long does it take?
Yes,
for the 24 hours and the 2 hours, like as a comparison?
Yeah. For the if I do the steady state simulations, they take, for example, approximately 45 minutes, let's say less than an hour. If I do time-dependent simulations every 24 hours, with magnetograms being updated every 24 hours, that will take approximately 1.5 hours.
Okay.
Not there is a big difference, not that big, maybe 2 hours. If I go down to 2 hours, it can take, I think, because it's been a long time since when I did it, it could take maybe 4 hours or 5 hours to run. It's still okay, but if you want results fast, it doesn't work.
And how does that compares to the solar cycle? I mean, if you're running this in solar maximum or solar minimum?
Yes, I haven't done specific study. I have taken different kind of rotations from 2018 onwards, where we have the PSP and solar orbiter after 2020 and so on. I mean that I have not done a systematic study to see how this differs, but it works better towards solar minimum because the magnetograms are simple. We don't have eruptive events. We don't have many active regions coming in and out. So it's much better on solar minimum again compared to solar.
Plus the fact that these are not vector magnetograms.
Yeah. Line of sight.
Projection. Yeah. Projection on the line of sight. So things are getting simple from the beginning in.
Right.
Simply. Easier at the beginning. If you take vector magnetograms, then
It will be more complicated?
yes.
Yes.
For sure.
I'm not sure how I should process, if I should process vector magnetograms to put them in the I should think about it.
You can talk with my knowledge. I mean, my knowledge is using vector.
Yeah, right.
Yeah. There is a technique to do that, but this will add
more complications.
More complexity to the whole thing.
Right.
Because at the end, all the model we are using to propagate from the photosphere to 0.1 AU doesn't really care. Okay, he needs only the values of the magnetogram. Doesn't really care what's the quality of the magnetogram. It's gonna be, but this could add more time in processing.
The point is that many things are simplified, right?
Yeah.
Even the so-called, well, we call it time dependent, okay, because of the updating of the boundary conditions, but it's actually a sequence of steady state, smaller modeling approaches that we interpolate between them. And we know it's simple, and we know the caveats of it, and we know the disadvantages of it. However, within its simplicity, we see that we can do better, and we see that we can explain things we couldn't do before. Even with this so far from perfect, oversimplification.
Well, that's the point. The point is to converge between the observation and the prediction.
Exactly.
If this is getting better and better all the time by adding things, then you are on the right track.
Yes. Right.
For SP prediction, even if we get all these nice solar wind or magnetic field lines, if we take them like 2 hours afterwards, something like that, it doesn't really work because, particles will be here in the.
Right, well, that's a good point that yes, thanks for mentioning
I
that.
don't know if you can, you understand what. So we can have something like a database of different scenarios.
Yes.
That we can just plug in and say, okay, this is going to happen.
This method, this time-dependent method is mostly, I said forecasting, but maybe the term was not super correct. When we're doing real-time forecasting, anyways, we take magnetograms every day, right? Today, I'm gonna take one magnetogram and run predictions, and the next day, the same. The way we're running that is, again, the simple steady-state way. What the real-time forecasting does not do is this interpolation within the heliospheric domain that we are doing, and we're doing that because we want to explain the physics that are taking place there. So indeed, this kind of stuff are not so important for real-time forecasting.
Yeah.
However, it would be very important for the physics once we have an old, for example, SAP event, to couple it with the model here and see what we get and try to explain things that were possibly not well explained or at all explained before. And I heard recently from the SAP event of the May 2024 that some people, maybe you know more than me, but I've heard from people that are doing SCPs that when they were trying to forecast, to model SCPs, the SCPs did not seem to reach Earth, but in reality, they reached Earth or Mars. I don't remember, but my point is that when I did my presentation and they saw it, they told me, oh, maybe it's because, it's not a perfect spiral. And they thought they would go there, but they didn't go there, and they go elsewhere. And maybe with the different directions and the different lengths of magnetic field lines, this could be explained.
Yeah, this period is very difficult because we have like 4 magnetic clouds, something like this.
Yes,
so
yes, indeed. It's very complicated.
It's very complicated.
Right.
But yes, you're right in that sense. Okay, do we have any other thing? No? Okay, let's thank Evangelia once more.
Thank you very much. I'm not sure. There are some questions.
No, it's not questions.
Okay. Thank you very much for attending, everyone. Ευχαριστώ πολύ.
Thank you, Evangelia. Oh. Θα το μαζέψω εγώ, βρε. Όχι, θα το κρατήσω.